man and that which concerns the intellectual. The first one tends to be robots, and the second tends to be more artificial intelligence. But of course, both involve some of the other at times. I happen to have been more interested in the use of machines to supplement humans rather than to replace them. The department has a very active program in robots. So I don't want to belittle it, it's just that my interest has been somewhat different. Machines have been essential in many areas. They enable us to manufacture things better. They enable us to get to the moon. There are all kinds of other things which we could not have done without them. And so one has to ask, how can they work and what limitations are there in the future, if any? Now I want to start back from the very beginning. The world is made out of molecules. Computers are made out of molecules. You and I are. The machine is made out of larger pieces called two-way devices, either memory or switching. And you're made out of cells. And these smaller units are put into bigger units for registers, control units, and you have bones and muscle and nervous system and such other things. From the smaller parts, bigger ones are made. Now I have to point out to you several times, I did last time, that from the small pieces there can be new effects in the large. Thus, friction. There is no friction among molecules, but there certainly is friction between objects such as that. You are well aware the difference between individuals and a mob or an army is quite significant. You're aware, I suppose, that committees can produce reports that no individual would have ever done. So there is a group activity which is different from the individual, and you cannot argue that since the parts don't have any intelligence, the whole cannot have it. Because if that were so, you would be hard put to have intelligence yourself. Now, I should also point out, when we do things in the real world, we don't do it the way nature did. For example, in flying, while Da Vinci studied birds, the Wright brothers really built a glider and put a power in it. We don't generally fly by flapping wings, although we built such devices. We built a couple of birds that flap wings, and one time in visiting Europe I saw a small plastic dove that you wound up with a rubber band and it flapped its wings and it would fly. I bought one and took it home to see how it worked. So we can make them fly, but by and large the airplanes you fly on don't flap their wings. They fly much faster than birds, they fly much higher, they do things differently. Furthermore, we depend heavily upon rotating equipment, round shafts, gears, everything else. Nature never invented a wheel that I can find. The heart, bang, 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 wherever you had a nice centrifugal pump, it would be nice and smooth. It would be far better designed, but nature was not able to do it. So by and large, we don't do it. In the telephone business, we want to communicate a long distance. We just didn't holler, or as they still do in the northern mountains of Spain, they have a whistling method. They whistle and it carries over from valley to valley and they can hear each other. And so they communicate that way. We did it differently. So when you want to do something nature has done, you often do it a very, very different method. Now again, if you want to look at what the human mind is, it's many, many components, many, many, many interconnections. And it's not homogeneous, it's different structure in different places doing different things. Various functions are apparently isolated in various areas. So the brain is a highly interconnected, large device with a great deal of specialization. It's not a homogeneous structure. Now, there are people who claim the reason why we have not been able to program a machine to think was it wasn't big enough. If we simply build a big enough machine, it could think. In fact, some believe if we build it big enough, automatically it will think, neglecting the fact, it seems to me, that somebody's got to program it at present. But then thinking may well be something that arises like friction. It is not contained in the parts, but it's contained in the whole. We really do not know what thinking is. Now I want to go back to a couple of the past achievements of what was done by AI. One of the famous ones is the isosceles triangle. This was a geometry proving theorem program. It would take problems just like you meet in Euclidean geometry as you met them and prove them. Now, if I gave you these two sides are equal, to prove the base angles are equal, most of you would bisect the angle, prove triangle 1 equal congruent to triangle 2, corresponding angles are equal. Some of you would have bisected the base and drawn the line and argued. The machine printed out triangle ABC is congruent to triangle CBA. Now you have to admit that's a nifty proof. It's got the elegance of mathematicians' life. The people who wrote the program had no knowledge of it. In fact, they said it wasn't known, which is not correct. It was in a footnote in my copy of Euclid. So it was known, but it's a very nifty proof. It's not widely known. It was not known to the people who did it, who wrote the program. So, did the machine produce originality? This is a point I've got to work on very hard. Are machines capable of producing originality? Certainly, if you've programmed machines very often, you've discovered the machine produces some original results you never intended. And in the case earlier I mentioned of the checker playing routine of Art Samuel, who altered his own programs, played games to see which programs worked better, and by experience selected the better and better programs, till what was a poor program beat the Connecticut checker champion. Now, if you watch the movie of that, it's very interesting. This guy is a very nice person. I won't say he's stupid, but he's a very nice, simple person who's played checkers all his life. And he's asked to play a machine, he's embarrassed. I mean, he should be playing with a machine. So he starts in with, he's polite, but he's got a supercilious attitude toward the machine. As the game goes on, you can see him changing his attitude, beginning to respect the machine. In fact, he begins to talk about the machine as if it were a real opponent. Like, that's a good move. When he finally lost, there's some more talk in which Art Samuel says, well, of course, the machine learned the program in a couple of hours, how to play a couple of hours of practice. He said, you mean, well, I took a whole lifetime to learn it, learned? Art says, yes. And you can see him being totally humiliated at that point, that a machine learned easily and defeated him. This move that made it must have been surprising. It must have had originality, just like that proof was original to the people. Now, if you look more closely at what they wrote, then you see why it happened. Construction is a very difficult thing to say how to construct a line. Given a geometric problem, what construction do you add? So they had asked the machine, can you prove it? And if you can't prove it, then here are some rules for constructing. Now, if I'd given you those rules, you might have found that nice proof with no construction. Yes, it was implied in there. But no, it was not. It was not put in consciously. It came out of an artifact. So, can you produce originality? Is not all your ideas traceable to previous experiences? Much of the time you have to say that when you examine closely. Well, it was something like that that suggested because I'd done so and so and so and so. Or that happened to me one time and I remembered. It's a very vexing question. The difficulty is, I've said before, the moment the machine does it, there's a program, and that isn't thinking. So long as you adopt that attitude, you are perfectly safe. Machines cannot think. But then you'll have to prove that you can think. Are you not the consequence of being loaded in with things? For example, when you took high school geometry, what was the teacher doing except putting a loading program in you so at the end of the course you could do geometry problems and you couldn't before? It's kind of hard to know. It's not easy to separate these things out. Now, the hard AI people, there are a bunch of AI people. The hard AI people claim that man is only a machine, a bunch of molecules, and that anything a machine can do, they can in time do. There's no essential difference in the intellectual world between machines and humans. There are other people who think there is a difference. I happen to be one of my old age. I was early raised as a physicist, engineer, and I tend to look at the world as a mess of molecules, and that's what everything was. And that has been the dominant theory of physics all the way down since Newton's time, or at least Dalton's time. I don't know how you feel about it. That's one way you're trained. On the other hand, I thought for a long while after coming here and decided self-awareness and self-consciousness were something too real to pretend that they were just imagination. I can dispose of free will. I can say, yes, I think I have the illusion of free will, but that doesn't mean I have it, because the sentence I've tried several times on you, you being what you are, the situation being what it is, can you do other than you do in the next minute? Scratch your nose, shift your chair, sit and do nothing. Can you do other than you do, you being what you are, the situation being what it is? There's no way of proving the theorem or proposition, so we have to go on. But it's a very awkward problem, because if you accept that you could not have done anything else, you're accepting strict determinism. You're accepting that everything that happened here now, these very words I'm saying, were preordained when the Big Bang occurred 12, 15 billion years ago. Now let me shift from the simple language things and mathematics. And we've written several ones. Let me see, I've probably missed some. We've missed several. Blind programmer at MIT for a doctorate thesis, a guy named Slagle, wrote a program for doing analytic integration just as you do in calculus. And he wrote it for the Whirlwind, which was an old machine. At that time, it was about as efficient in machine costs as humans, and about as versatile as a sophomore at MIT. Since then, machines improved greatly, the programs have improved greatly, and now there are like integration programs. We integrate just like you did. The integral cosine is minus sine x plus c, does the same thing. Much wider range than you can, and some are said, I have not examined them, but I've told that some will either produce the answer in closed form or else prove to you why it cannot exist in closed form. One of the earliest ones was calculating derivatives. Derivative, in case you forgot in calculus, is a very straightforward process. It's an algorithm. Do this, a derivative of product of some quotient, you're going to learn all those rules. What you tend to forget is that all the stuff you did afterwards, the simplification, was not part of differentiation. You simplify afterwards. So we wrote programs to differentiate, and one of the very, very early ones, because we wanted to get a power series of a function about a point, and so we let the machine differentiate 19 times, and evaluate those expressions, and that gave us the first 20 terms of a power series. That was done very, very early. The analytic integration was in the 60s. We've done these things. We have algebraic packages that do things. I'll come back to those in a little while, I guess. I want to shift to some other ones. At Bell Laboratories, early on, we looked at the question of producing music. Max Matthews and John Pierce were particular ones, but other people were involved. Now, in case you don't know it, haven't thought about it, when the sound pressure falls on a microphone, there is a single pressure. So the most complicated piece of music you've heard is at any one moment a single air pressure. All the various components are added together. So you can picture music as being a single track in time. Now if I sample that thing equally spaced at twice the highest frequency present, that suggests something like 36, we actually use about 42,500 samples per second. And if taking those samples, I then quantize the numbers vertically to a small amount to get a definite integer, I then have a string of numbers which represents the music. I can play that string of numbers back through an analog digital converter with a small amount of a filter, and I can get the music back again. And that's in fact what you have on many of your instruments now. You have digitally recorded music. We don't do the analog the way we used to. Well, the question was, can we not make the music without the instruments? For example, I want a pure tone, I simply write a program for a sine. And the numbers coming out of the sine give me a pure tone. If I want a pattern of several sinusoids for the fundamental and harmonics, I write several terms and add them all together. If I want to simulate a more sophisticated instrument, I put in something for the attack. How does the volume rise and how does the volume fall? And typically you put exponential factors in for a while and you get the sound. Now we had at Bell Labs when I was there for a while a fellow from France who happened to be an expert on the French horn. And he was in the Department of Acoustics and he was interested in simulating, could you simulate a French horn? Now remember, he's an expert, he knows just how it sounds. He finally produced a tape in which there were some tones which he had played and some tones which the machine had calculated. And you couldn't tell them apart. He could simulate a sound. Well, this was the idea they had. They had, if you give me the pattern of the musical instruments, what you want, what's the attack, vibrato, everything else of the musical instrument, and if you give me the music and I assign to each one the ones, then I can have the machine calculate leisurely what the height of that curve will be, put out those numbers, and then at a uniform rate play those numbers in. Lo and behold, I have music. Thus the composer can hear the music that he is composing on whatever instruments he wants to pick. In the past, composers often had to wait years and years and years before some of their early compositions were ever heard except in their own imagination. Now, from reading journals on computer music, I seem to see that almost all composers have elaborate computer layouts in which they simulate the music all the way along. The next question arises, if I have to supply the notes, why do I write a program which will compose music? And there have been a bunch of those. There was Iliac Suite had written at Illinois and various other things, composed according to classical musical formulas for composing. I say as a result of these things, we are now in a position of, in a technical sense, disposing of music. Any sound that can exist can be produced by a computer. Anything the composer wants, he can have. A conductor can go over a passage when he's doing with real people, and he can go over a passage 2 or 3 times. One time the flute is in a little late, next time the violin is a little too loud, and so on. He finally settles for what he can get. With a computer-produced music, the conductor can get exactly what they want. They go back over the thing and change the formula for a millisecond coming in here or that. They can get precisely what they want. So the problem has been now removed from can I build physical instruments and can people play them to what sounds are worth listening to. That's the problem now in music. Technically, we have solved all the problems. We can make any sound you want. We can do it any way you want without trouble. The problem is what sounds are worth listening to. And that differs from person to person. There is a tendency still to cling to the old instruments and think that they were best. But there are gradually things like the Moog synthesizer and synthetic musical instruments, which are strictly not classical instruments. And we're moving that direction. Much of the music you hear on TV on commercials is computer produced. They can get just what they want the way they want. So we have there done something which I claim is the interesting part of computers. We have taken away the physical side and put it right smack on the intellectual side. What sounds are worth listening to? Now you can imagine, if you want, that you have a style of music you like. And you can have a program there and it plays background music. I'm not talking foreground music, I'm talking background music in your house. And when you like the foreground music, you occasionally punch, I like it, or you punch, I don't like it. And the formula, like the checker playing routine, adapts to what you like. And so you can have music supplied background in your house of the type you like, just to suit you. It's not much more than the machine just going along happily, doing calculating, putting out the numbers on a soundtrack, and the soundtrack being converted to music. You can have these things. Now, I'm not saying I can do foreground music. When I listened to the music composed by machines, remember, I'm not a musician. When I listened to that stuff, I didn't think it was very good. Now, I don't know what they're doing now, but computer-composed music has never struck me as very good. Computer-made music from the notes is something else quite differently. Now you might ask why Bell Labs is doing it. Pretty obvious. The Bell Labs was concerned with sound, and music is a more pleasant way of coping with the problem of how do you make sound. We've gone on to doing various ways of synthesizing human voice. We've done it completely from formulas. You just read the words and we have nothing there, or we've done another thing. We've had a person pronounce a bunch of syllables, here, there, and yon, and we take the input stuff, break it up into syllables, and we blend these parts together. We sort of fade one into the other, and we slur one the other way we know, and so we have somebody talking. The person behind it said all the individual syllables, but what you were actually hearing was never put together in that sequence by the speaker. You very often hear that. Many synthetic voices are running around, and there's nobody behind it saying it, particularly if it's a wide variety of things. Now, I'm more interested, as I say, what machines can do with us. Like in music, it has solved the problem in some sense. Now, computers compete with humans. They've displaced them a large number of jobs, and many, many years ago, on a panel, there was discussion of this matter, and somebody from the Bureau of Labor Statistics said a lot of things, and I got up next and said, so many people have been employed in computers, and they've made so many new jobs, and so many jobs have been obsoleted. There is no way you can possibly compare one or the other because it's too vague in both cases. But what you can say, I said, was there's a tendency for computers to do the simple jobs and not the hard ones. So there's a tendency of people who are doing simple jobs to be obsoleted and find no job. Now there's a desire on everyone's part that these obsoleted people can be trained to compete with machines. There's a very great desire that you can take people who are not very bright, nevertheless we can train them so they can compete. On the other hand, I have said in the same speech, I did not believe that you could take coal miners and make them into first-class programmers. I have my doubts about this wish to believe that we can take anybody and make them, find a job for them which they can compete against machines in the next 100 years. It's presenting us with a very interesting problem. Not that machines do all the simplest ones, but they do a lot of them. To give you a simple example, I worked nights for one summer at a factory. In the factory there was a little lady who was there all night long who dispensed coffee and donuts and other rolls and candy. Well, such ladies are not employed now. We have machines for coffee dispensing and other things. There isn't that job. When I was young, there were elevator operators who ran the elevators up and down. Now you haven't probably seen an elevator operator for a long time. We have in fact invaded the low-level jobs quite well, all things considered, but we haven't done a lot of them. There's a lot of them still left that too hard for us to do as yet. But one suspects we'll do it in time. It's a very interesting problem that's going on, and I don't have the answer. But it's a problem which you'll be concerned with in your life. To what extent are you going to obsolete people in your business? If you obsolete them, you will find the lower levels be obsoleted. Then you could ask yourself, what are these people to do in our society? If there's no job at low level or very few jobs left at low level, we're going to have a problem on our hands. And you might as well recognize that it's part of the problem of mechanization. Now back to games, geometry, and such other things. We have algebra programs, but algebra programs did not work out. You would think we could have done algebra, but let me point out to you what happened. There is a word called simplify. When you ever had problems, simplify. The calculus book said differentiate and simplify constantly. Well, when the new math came by, one of my friends was on the committee and they came around with a definition, and so I looked at the definition and said, well, 1 over the square root of x plus 1 over the square root of y is not simple because it's the sum of two terms and the radicals in the denominator. You want no radicals in the denominator. What you want is the square root of x, the square root of y, square root of x plus square root of y over xy. That's simple. That's simple, that's not. Obviously, by their definition, something is wrong, right? The difficulty is quite simple. That's a bad slip-up. If you are going to do integration in calculus, you try and break the thing up, simplify it into a great many terms, so you can integrate term by term by term. If after differentiating you're going to try and find some zeros, you try and get it together into a product so you can find the zeros. Simplify depends upon what you are planning to do next. There isn't any word, despite the fact the books in mathematics always said, do this and simplify. They never told you what really simplification was, and that definition they made gives nonsense like that, which obviously is not correct. Therefore, although you might think that we could do algebra, we have not been able to do algebra the way we had geometry. We had this program in geometry, which did high school geometry problems. No trouble. We have something instead called directed algebra, I'd say. You tell it to do this. You say, differentiate that. Out comes the derivative. You say, set equals 0. It rearranges. Find the zeros. Well, it can try to find them. Or you can say this, that. You direct step by step by step. Substitute this expression in that one. Or eliminate x between those two equations. Directed algebra, we have powerful packages to do this. Quite a few different ones. They are very effective. They will solve some larger pieces like find me the solution of these 17 equations and 17 unknowns, all linear. Yes, it can do it. Usually it's numerically they could do it, although sometimes it does it algebraically as well. There's a little difference between the two of them. Now we have similar ones for chemistry, for synthesizing compounds. Chemical companies want to make things. They synthesize. The synthesis program, the guy says, well, try making it this way. And the machine keeps track of how long it will take, how expensive the ingredients are, what the yields are, and such other things. And when the various costs of the raw chemicals change, they may go back and try and synthesize the same compound by another path to see if it's cheaper. We do that quite successfully. Again, it is directed synthesis. Try that path, try that. You don't ask them, hey, synthesize that with no clues. We haven't found we can do that trick so well, but directed stuff, the machine is a big, big help. Now, in the form of robots, computers have invaded production lines very well, and I told you repeatedly they do a better job, they make a better product, cheaper, but it's a different product. Screws and nuts are replaced by welds and rivets. You must learn to do a different job. You accomplish the same end, but it's done in a rather different way if you're going to be successful. Now, computer chips, as you know, are designed by machines. There is some artificial intelligence in how to lay them out on a chip. You, as a chip designer, want to put the storage, the memory over here, and you want to put the arithmetic unit there and so on. You give it some larger direction. But the famous Pentium chip you read about with bugs on it, probably the details of the chip never passed through any human mind. When there was trouble, we could dig in and find out some parts and locate where the trouble was. But the millions of interconnections, no. So we are designing chips. We are manufacturing chips by machines. And in fact, one company, my friend told me, he ordered, finally after a great deal of discussion, they ordered the university a half a dozen machines with such properties. They were not all exactly the same. The order went in that afternoon. That night, the plant built them. And the next morning, they were on a shipping dock ready to be shipped. They were assembled by robots during the night. So the machines were designed, assembled, and shipped practically by machines. We are doing this enormously in our society. And it's working out pretty well, pretty well. Now, when in an area where there's no chance for surprise, robots are pretty good. When there is room for surprise, then robots are not so good. Thus, I told you, trying to put a nut on a bolt, usually it goes on, but sometimes it gets stuck, and you're surprised. And what you do then is very interesting, just try and figure out how you decide to get the nut on the bolt. You try this, that, and the other thing. Designing a machine to do that would be very, very hard to manage. But you somehow or other have learned how to cope. So when the surprises are available, robots are not too red hot. But when there's no surprise, robots are very, very good. Now, an observation for Davy about doing things differently. Suppose you decide you want some mobile robots. Instead of having them walk on the floor, if you have them run from tracks on the ceiling, then several things happen. During battle or other times when things fall on the floor, the robot doesn't have to step around it. He just goes happily above, unless it's very high. When the ship rocks a lot, the robot hanging from the ceiling doesn't have as much trouble balancing as he would on the deck. Now, that's still the same job, but you see what I mean by saying you do it differently. Instead of moving your robots on the floor, you say, well, why don't I move the robots from the ceiling? Maybe, I'm not saying it is, maybe that would be a better idea. That's the kind of a thing you need to do in many times in trying to mechanize any particular profession. How do you do it? By doing it, getting the same result, but doing it in essentially a different way, which fits the machines better than fits you. Now let's go back to chess. Chess was originally thought to involve thinking, and all of us in the beginning thought that it did. Now I'll tell you something you may not know. During the Second World War, the Dutch were occupied, and some Dutch chess players got together and studied the question of how they played chess. And so the masters were gave out to the psychologists a description of what they thought they were thinking. Now they had a particular board position which they asked them to play. If I show it to you, you probably make some of the moves. There is one really good move, and once you see it, you know that it's good. But until you see it, you don't. Well, what happened? The very best chess players all saw that move and looked at about 100 different moves. The second-rate ones looked at about 100 moves and didn't see it. Think it over. The experts all looked right the first time. The second-rate ones didn't look at the right place. Now, a good example of that among human beings is this guy, Claude Shannon, who invented information theory, a very bright guy. We went down to his office one time, several of us, with a problem in number theory. And we started talking about it. He said, wait a minute, get this straight. He steps up to the blackboard. As we talk, he draws a picture. When we finish talking, he sits down. We look at the picture and say, thank you, Claude, walk out. He had the gift of looking at the problem right the first time. Lots of us look at the problem 10 times before we find out how to do it. It's obviously something about style which totally eludes us as to why the experts do it. Again, Fermi. You give him a problem, he would start writing on a blackboard and he would start making the correct derivation. You give the problem to Teller, he would fumble around 16 times, but he'd come up with the answer finally. But Fermi had the gift of just looking at things right from the beginning. What this is, we don't know, but it's what I'm trying to teach you in this class. How to look at the world efficiently rather than blunder and blunder and blunder, and then finally find it. It's clearly better, but we don't know. So we thought that chess would be a good thing. Well, in spite of somebody saying a chess master of the world will be done in 10 years by a machine, it's been about 50 years almost, no, 45 shall we say. And every year the ACM has a contest of chess playing programs that are getting better. And I think it's only a question of time now until, if the masters will play the machine will beat the masters. There is a story that in backgammon, a contest in Italy, the program took on all the guys afterward game and beat them all, every one of them. Checker playing is clearly better by machine now than humans. But you see there's something wrong. First place, now there is a program, you see how it's done, you're a little dissatisfied. But more, way it is being done is millions of board positions are looked at every second. Humans, in all their time while they play, they look at maybe 100 positions. We are not playing chess the way the chess masters apparently play. We don't know. We only have their stream of consciousness. But we have the fact also that the experts looked the right way the first time. We didn't do this. We simply killed the problem by excessive computation. And we probably already have machines fast enough to beat the average and even very classy chess. So the chess master of the world may well be, if they allow the thing to happen, a computer. They may very well debar from the actual game, but they may still play with them afterwards to see how it comes out. I don't know. So you have a problem there with chess. It wasn't done the way we thought it was, and many of us have become dissatisfied. We thought it was going to be a study of how the human mind works. And that is one part of AI. There are a group of people in AI who are concerned with simulating how we do things rather than getting the thing done. There's another bunch who only want to get the result. And that's the typical bunch who are now dominating chess. There were a few chess programs which tried to do it the way humans did, but they have not proved to be powerful. The ones killing with computation have won out. There's another bunch of people in artificial intelligence who think the things are optimization. They merely think problems are optimization, and that's not necessarily what it is. Now, there's a claim I have to go through about randomness. There is a claim that randomness contains all knowledge, and it's based upon the story you may or may not know about the monkeys in the typewriter. The statement is that if I put a bunch of monkeys in a typewriter, wait long enough, the monkeys will type out all the books in the British Museum in the order in which they appear on the shelves. And the argument goes as follows. Sooner or later, a monkey will hit the first key correctly. Indeed, in infinite time, the first key will be hit correctly infinite number of times. Now, among that infinite number of times, there'll be times when the second key is hit correctly. And that will happen an infinite number of times. And among those, you see the rest, right? You shouldn't hold your breath until the whole thing happens, but the argument is that given enough time, the monkeys would type out the whole British thing at random. And the same sense is that if I could recognize information, I could connect up to a random source and wait, and sooner or later, the next theory of physics would come by, and there I'd have it, if I could recognize it. If I had a filter which would recognize knowledge from noise, it is said that white noise contains all knowledge. Sooner or later, every piece of knowledge you have will come down that doggone random source. Well, don't wait. And all methods of AI which depend upon randomness to get you through are likely to have horrendous lengths of time to wait. Now, there's a claim I said several times about you having free will, and that's a very, very hard question. It's an awkward one. Now, there's a tacit belief in this. I told you the other day that you treat your children as a combination of free will and not free will. You believe if you raise them properly, they will have to be proper people. And there is a belief among many people that if I only clean up the slums and put them nice, the people will be nice. Against that argument I once gave long ago, I said if New York City can be magically cleaned up tomorrow, all the potholes fixed, all the subways painted and everything else nicely, how long would it take till you're back where you are right now? Because you won't have changed the people. And so there's a belief that the people being what they are, they cannot necessarily be changed by the environment very easily. We have very, very mixed beliefs. We have beliefs on one side of much of our social welfare that if we only do the right thing by them, they will have to behave properly back. And there's the other side that we don't really believe it. We're mixed about the matter. And it bears on machines because it bears on the same question to what extent machines have free will, what extent people can be changed. Can they act, do they have free will to act the way they do, or must they act the way they do because of previous conditioning that caused them to be that way? With regard to your pets, you sort of believe if you raise your pet dog or cat that it behaves that way because of what you treated in the past. With your children, you're ambivalent. And with life in general, you are ambivalent. I want to go on and talk about the enormous variety of AI. There are those who think that they are studying the human being and trying to duplicate that. They are simulating. There are those who are merely trying to produce the result. Those are hard AI. They only want to get the same result, and they claim if the result is the same, it must be the same thinking. But earlier I gave you the argument that when a child is multiplying 2 3-digit numbers together, and I watch them, I think the child is thinking. When I do it, it's a conditioned response. When a machine does it, I don't think it's thinking at all. So maybe thinking is not what is done, it's the way it's done. The second story I told you was my attempt to find the smallest program which would include thinking, such that if I cut it in half, it wouldn't. And my conclusion was that perhaps the question is the wrong question. That maybe thinking is not yes, no, it's a matter of degree. Now these bear on the problem you face Thursday. Thursday you are discussing, can machines think? Furthermore, you're sitting down in the front rows so the camera can see you. You don't sit back there, we're sitting in the front rows. And you have to talk about it. Now I will say again, I don't care what you say, it's not my business. My business is you say what you think clearly and have an idea of what is what and can express yourself. Previous time to giving this course, the students, many of them said, you know, that in some respects was the best lecture of the bunch. Now you can drift into, from machines think, into the second one, which I'm going to condense two lectures into one. How can you mechanize further your particular field of activity? I don't want to hear how it's done in the past. I want to know what new applications might well be done. What would be the trend? How will your organization get machines in? Not just count them, but what innovative new ways which are desirable can happen. So you've got a problem on your hands for the next 2 days. Getting yourself ready to be articulate and furthermore finding out what you think. Remember the problem. If the machine does it, there's a program, you probably are going to deny its thinking. And is that reasonable? Is it really reasonable? If you're going to do that, then you're like that Jesuit guy we had. Thinking what humans can do and machines can't do. If thinking cannot be done by a program, then of course machines run by programs cannot think. That would settle the question. But it doesn't seem reasonable because you can't prove very easily that you yourself are much different than a machine, conditioned by great many responses. You're born with a certain amount of stuff as you're born. Something like a machine is born with a bunch of instructions it can follow. And we put on top of it higher and higher level languages. You gradually learn more and more things. Magically you learn languages and such other things. But there are parts in you who are built to master languages. And the thing is, the part that will master language doesn't matter much what language it is. If you're raised in China, you'll learn Chinese. If you're raised in France, you'll learn French. The same mechanism can learn language. You're built in with some kind of a device there that apparently will cope with languages. And learning the first language is very different than learning a second one. The first one is truly amazing, and many of you have been watching your children as they grapple with the problem and finally learn. There's something in you partially organized to do this. There have been experiments with the apes and so on, and the claim was first that they didn't have the voice, but I think there's a fair average consensus after all the hoopla and so on that the nearest relative apes don't have a language device in them the way we have a language. They have a more primitive language, but it's by no means as rich as ours. They do have a language. They have various sounds for warnings of this type and the other thing. Even mice and so on have warning languages. So there is some language, but it's not the way we mean by a very rich language with abstractions and such other things we have. You have many other things which are built into you so you can do things. They are hardwired into you, and on top of this initial hardwiring is your ability to speak English or French depending upon the environment you live in. So the environment does control. Your ability to speak a language depends upon where you were born and raised. Are you sure that you have free will, that you could speak any language you want? No, you can only speak the language which you were first raised in. Later on you may acquire other languages, but fundamentally you learn that language, or sometimes some of you may have been raised in a two-language household, which does cause children to have trouble at times. But by and large, the language you learned was a function of the environment which you lived in, and therefore, did you have a choice? Could you speak the other languages? No, it formed you. It's a very difficult question. I want to leave it to you to worry about, and I remind you, next time we're down the front row, and if you people won't talk, I will produce my little list of students and say, so-and-so, start talking. Okay, see you Thursday.